Thank you, Rachel. And thank you to all of you for joining us today. Welcome or good afternoon, depending on where you are in the world. And happy St. Patrick's Day, a day of celebration, which is what we're going to be doing today in the first of our new research series webinars, asking about how technology can transform lives and make our communities safer, more sustainable, and more equitable. Today, I am very humbled to be joined by three esteemed thought leaders, some of the top research leaders in our country, to talk about the latest in future technology research, specifically focusing on how their research and their institutions are looking at some innovations such as autonomous vehicles and connected vehicles. Today, we're going to hear from three amazing folks who will help us learn about how connected and automated research is impacting day-to-day lives and the future of mobility. And we'll also understand how the development of these research technologies that their teams are working on can advance future transportation solutions. Today, we are first going to hear from the amazing Lily Eleftheriou, who is a PhD researcher and director of the University of Florida Transportation Institute. Lily is also the Barbara Goldsby Professor of Civil Engineering at the University of Florida. Welcome, Lily. Next, we will hear from Henry Liu, who is not only on our board of directors here at ITS America, but Henry is also the director of MCITY, the Michigan Public-Private Research Institution, really devoted to transforming mobility. And he's also professor at the Department of Civil and Environmental Engineering and also one of the key U.S. Department of Transportation's University Research Centers on connected and automated transportation. Last, but certainly not least, also an ITS America leader, board member, and advocate for our work is Greg Winfrey, who is the director of the Texas A&M Transportation Institute. Greg, like the other two speakers today, needs no introduction. He is the director of TTI, the largest research institution on transportation in the United States. And he's also been appointed to lead the Texas Connected and Automated Vehicle Task Force, showing his leadership on these topics. So today, everyone, we're going to hear briefly from each of these amazing leaders and researchers on the work that they're doing. Then we're going to introduce some probing questions and, of course, finish with a great discussion from you all. So start to think about the questions for these researchers today. And with that, I'm going to hand it off first to Lily, who's going to talk a little bit about her research. Thank you and welcome, Lily.
Thank you very much. It's a great pleasure to be here. And I'm going to present on the iStreet Living Lab and the research that we've been doing. I'm going to give some examples, particularly related to traffic management with CAVs. And then I want to talk a little bit about some of the challenges with working with CAVs. Next. So first of all, what is iStreet? It's a living lab, which is a collaboration between the University of Florida, the Florida Department of Transportation, and the city of Gainesville. We have been looking at connected autonomous vehicles, but also applications related to transit, micromobility, bicycles, and pedestrians, and data analytics, and a variety of other topics. The objective, and because of our partnership with FDOT and the city, is to have research to deployment to evaluation type of projects. So we have been looking at connected autonomous vehicle type applications in Gainesville, but we are also collecting data across Florida from different locations. Next. The picture here shows our map of devices around the Gainesville area, and I'm providing here the website. If you have an interest, you can go in and check out all the different devices, their location, and what their functionality is. The map here shows our roadside units, which are along I-75 freeway locations, as well as arterials. Next. And this map shows the data locations where we're getting information from a variety of applications across Florida. This map is a Florida Department of Transportation map, and the yellow stars show where we're getting data from across Florida, in the vicinity of Gainesville, of course, but also along the I-4 corridor, and then the Florida Keys. Several other locations are underway. Next. And this map shows a little bit more information about the roadside units around the Gainesville area. We have about 150 around I-75 and around the city of Gainesville. We have roadside units at 13 signalized intersections, looking at 7 mid-block crossings, specifically addressing issues for connectivity with pedestrians. We also have applications related to signal control optimization, and we have about 60 connected vehicles. The vast majority of them are with the UF fleet, and therefore the objective there was to make sure that we have multiple vehicles in one location. So the area of Gainesville is more contained than your typical metropolitan area. So 60 vehicles go a long way to have multiple vehicles at one location. There are several vehicles that are belong to the city of Gainesville and some for FDOT. Next. So one of the applications is an autonomous shuttle, which runs in the downtown area. The video here is showing the shuttle when it was mapping the route. And you see here how the shuttle was getting ready to pull over and how it stopped when the bicyclist went through. The shuttle is now in the second phase of operation. So it's been running through the downtown Gainesville area, going through a traffic signal. We work very closely with our industry partners to make sure that the vehicle was also receiving signal information. And so we're able to coordinate between the infrastructure and the vehicle. Next. One of the studies that we've been doing with autonomous shuttles, and this one is showing the one in Lake Nona, close to the Orlando area, is to understand how the vehicle moves, and from that extract information that helps us model its movement. The reason that we want to do that is then once we know how the vehicle itself moves and how vehicles around it move, then we can model it in simulation and evaluate the impacts in other locations. So that has been one of the primary objectives for our data collection in Lake Nona. We've also looked at traveler perceptions and what how drivers react to the shuttle, how travelers generally react, and we did a before-after survey. Well, the good news is once people get exposed to the autonomous shuttle technology and they're able to take the shuttle and all that, they feel much more comfortable with autonomy. So the perception becomes much more positive. On the negative side, for drivers following the shuttle, they get really annoyed with the low speeds, and of course that's an artifact of the technology. Right now the speed of the shuttle is relatively slow, and so it's important for others contemplating a deployment for the shuttle is to consider how other traffic around it is going to react, because one of our observations was that vehicles were following the shuttle were passing illegally. They were passing from the opposing direction when they were not supposed to. So things to watch for with autonomous shuttles. Next. One of our applications along I Street, and this is an intersection on campus, is to provide optimal trajectories to vehicles that are able to receive it, and at the same time coordinate signal control. Now, what the video is showing is the optimal trajectories that we send to the vehicles versus the type of trajectory that the vehicle is able to follow. So we developed algorithms that allow us to maximize the throughput and minimize travel time by controlling the autonomous vehicles, because autonomous vehicles can receive a trajectory and execute it exactly as it is sent to them. We also have developed an app that allows a connected vehicle or even a conventional vehicle to follow speed guidance and be able to get to the stop bar at the maximum speed at the minimum headway, and that allows us to maximize throughput. Next. I just wanted to quickly show an example of that shows the visualization of, and there's a video here, if you can click on the video. The top shows what happens when you have autonomous vehicles, the bottom when you have conventional vehicles. And what we did here is we changed the trajectories of the vehicles for autonomous vehicles to create gaps for traffic coming on from the ramp. And so we've developed several different types of such algorithms for freeways, for roundabouts, so that when you have full control of the traffic, you can really increase the throughput. You're taking advantage of gaps in a much better way. You're taking advantage of the pavement in a much better way. So this just shows a visualization of how that would work for a merge area. Next. Another project has been to provide warnings to drivers about the location of school zones and about the location of bicyclists. And we've used eye tracking technology to see where the driver was looking at when they were getting that type of warning. So just another type of application for connected vehicles. And the experiments have shown significant improvement with specific auditory and visual cues for the driver. So promising for safety. Next. As I said, we have a data analytics interface which assembles data from the more than 30 research projects that are ongoing or completed. I just covered just a few of those, but we have data that are coming in from several locations across Florida. And as we have additional connected vehicle deployments across Florida, we expect that database will increase. And so we're working with our faculty in computer science to put that together. Next. And as I close, just wanted to highlight some of the challenges with the iStreet Living Lab. First of all, implementation is much more complex than theory, than simulation. The issues that we run into include sensing accuracy, location of vehicles and so on, reliability of the equipment, accessibility of data from different partners, because we're bringing in several different industry partners, and the data that we need for specific applications are not always available. The coordination among multiple diverse partners, from the public agencies to private industry, and generally the complexity of the system when we have humans in the loop. That is what makes our jobs so challenging and exciting. So with that, next one. Just my contact information, and we're always looking for more collaboration opportunities. Both the FDOT and the City of Gainesville are very interested in further partnerships. So with that, I'm going to turn it over to Henry Liu. Thank you.
Thank you, Lily. My name is Henry Liu. I'm from University of Michigan. So the topic I'd like to discuss today is on the safety challenges for automated vehicles, particularly to look at what are the problems that has hindered the progress of automated vehicle deployment, and then briefly discuss our research projects at the University of Michigan that help address some of these issues. And next slide. So in the last 10 to 20 years, automated vehicle has been a really hot topic and attracting billions of dollars in investment, as well as significant interest from academia. And around 2016, a number of companies has announced that there will be mass production of automated vehicles by 2020. And we're now 2022, we don't see any of these commercial available consumer level of automated vehicle yet on the market. Next slide. So what are the problems? And obviously the reason for that is multifold. But above all, I think it's the safety gap between human drivers versus the automated driving systems are still there. If you look into the performance for human drivers, my experience, one accident per roughly about 1 million miles. But if you look at automated driving systems, according to California's disengagement report, on average, one disengagement every about 10,000 miles. And so the safety performance, the gap is about 2 magnitude of differences. So that's still very, very big before this automated vehicle really can be deployed. Next slide. So why the safety gap still exists after so much investment on it? And in my opinion, I think we have two grand challenges, technical challenges for automated vehicle. And the first one is what I call the curse of dimensionality. This is really being caused by the complexity of the driving environment. And so the driving environment could be so complex because of different weather conditions, different road infrastructures, and different road users, and each of the road users has different behavior characteristics as well. If you combine all these together, the driving environment could be very complex. But the good news is that in the last 10 years, the deep learning model has been developed and being utilized to handle these complex driving environment. And that's why people are so bullish at the time about 5 years ago that we might have mass production of automated vehicles in a few years by 2020 also. Next slide. But if you look at the next challenges for automated vehicle, and this challenge I call it curse of rareness, is really caused by these long tail, low probability, safety critical event. And in the right hand side, if you see this video, the video shows that the automated vehicle crossing the intersection and having the yellow the green light, so they have the right of way, but in a cross street there is an emergency vehicle coming in, and so this vehicle has to really give the right of way to the emergency vehicle, and then after that vehicle passes, this vehicle can go. So this type of low probability scenarios, but they are safety critical, and so if it's not handled well, that might cause crashes. And so so if you look into the left, most of the situations the automated vehicle will experience are these normal driving scenarios, and and those scenarios can mostly handled by these deep learning models, but the deep learning model has difficulty to handle these low probability safety critical type of event. And in the figure I show you the current state of the art automated vehicle performance, so that's what they still have quite a bit of distance between the current state of art automated vehicle versus the human driver in terms of safety performance. And on the other hand, if you look into the development cost for automated vehicles and to handle these safety critical event, the probability is low, but for this type of event, but the development cost for those to handle this type of situation is increased exponentially. So it's not that easy to handle this type of event. And that's why we do not really have commercial available highly automated vehicle yet. And next slide. So what do we do at the University of Michigan to help address these two challenges for automated vehicle? And one of the things related with, particularly on addressing the challenge for the curse of rareness, is to provide data from the roadside and then to complement the onboard sensors to reduce the corner cases or the low probability safety critical event. And so that's why we started this smart intersection project last year. And this is a project, in this project, we will equip about 21 intersections in the city of Ann Arbor, and each of the intersection will have a number of sensors that will detect and track and predict the object locations and trajectories, and provide that information through the sensor data sharing messages to automated vehicles. And hopefully we can reduce in terms of these unexpected situations for automated vehicle to accelerate the automated vehicle deployment. So the goal for this project is to develop an infrastructure assisted cooperative driving automation testbed, and so that the automated vehicle developer can utilize this testbed to test their automated vehicles. And a number of leading industry companies are working with us on this project. So next slide. So part of this project is that we have instrumented a roundabout in the city of Ann Arbor. So if you play the video, and so on this roundabout, there's 4 grid smart cameras and 4 flare thermal cameras and 2 Econlight IQ scan radar. And I just showed you this grid smart cameras. And so we developed the object detection tracking algorithms, and then we also developed trajectory prediction algorithms, and then superimpose these detected objects on the right-hand side, the maps. And the green balloon associated with each individual vehicle are essentially the predicted trajectories and in the next 2 seconds. And so if when the balloon is bigger, means the variance for that prediction is bigger too. And this is a roundabout in the city of Ann Arbor across State Street and Ellsworth Road. And this paper is going to be presented in the International Conference for Robotics and Automation this year. And if you go to the next slide. And just for your interest, I want to show you 2 of these interesting events, and we actually identified with 3 months, we identified 15 crashes at this roundabout and about 210 these near misses at the roundabout as well. And the one I want to show you is on the left-hand side is a crash occurred in last September. As you can see, the arrow point was the crash occurs. And that's because one of the vehicles, actually outer lane vehicles, not supposed to do the left turn, but they did the left turn, and the inner lane vehicle want to get out, and that's why they get the right angle crashes. On the right-hand side video, at a similar location, you will see this near miss event. It's not a crash, but it's near miss. So there's number of these event has been identified and being collected and stored in our database. We're looking into this event and trying to learn from these safety critical event to see how we can design our planning modules to avoid this type of situation. Next slide. So the next the other project we're working at University of Michigan is to utilize M-City as a test track and to develop our mock on-road test. It's well known that the public on-road test is necessary, but it's also very inefficient because it needs billions of miles to certify the safety performance of automated vehicle. So what we do is we utilize our closed test track at M-City, but complement that test track with augmented reality, meaning that we will use simulated vehicles as background vehicles and to supplement the physical facility that the automated vehicle will run into, so that we can utilize this simulation to generate all sorts of scenarios to accelerate testing and training process. And so that's why we developed what we call naturalistic and adversarial driving environment to supplement with these test track. And one of the things I want to mention, particularly to transportation researchers, is that when we develop our augmented reality utilizing simulation models, one of the things we find out is the current traffic simulation models, mostly developed for traffic flow analysis purposes, they cannot be utilized for testing and training of these automated vehicles. And just give you one simple example. And so in the bottom figure on the left, these are the trajectories collected from ground truth roundabout data. And if you simulate and calibrate it, utilize this open source sumo model, that's what this shows. And you can see, obviously, the spatial distribution is very, very different. But it's critical when we talk about safety performance of these automated vehicles. That's why we developed a new set of naturalistic driving simulators, and not utilizing the default traffic simulation. Next slide. And so this is, if you play the video, so this is what we do when we do the MOOC, so-called MOOC on road test. On your left, this is a simulation. This is a sumo simulation. We replaced the internal model with our naturalistic driving environment simulator, and we still utilize the graphical user interface. The red car is essentially the real vehicles running in the test track. All the yellow cars are simulated background vehicles. And these background vehicles are, the information is being packaged into basic safety message and broadcast within the physical facility so that the real vehicle under test can receive the background information. So on the right-hand side of video, on the top, that's essentially the vehicle running within the test track. And then you can see that's empty, but below that, there's a synthesized view of this vehicle. And because we're providing the simulated vehicle information to the automated vehicle as well. And in the middle, that's from the RUS visualization tools. You can see the black car is the automated vehicle under test. All these boxes are simulated vehicle feeded to these automated vehicles so that you can generate different type of scenarios and to challenge the automated vehicle and to see how they react to it. So these are the two projects I briefly discussed, and that's I think if you go to the next slide, I want to thank you very much for participating in the seminar. And I'm going to give the floor to Greg Winfrey to present.
Okay, thank you so much, Henry. Greatly appreciated. Sorry, I'm getting a prompt that says host is asked to start the video, so I have done so. It's a great pleasure to be here with you all. I'm Greg Winfrey, Agency Director for the Texas A&M Transportation Institute. I'd like to give a great thanks to Carlos, Rachel, and Kristen for inviting me to participate in this webinar today. I'm also pleased to join my esteemed colleagues and friends, Lily and Henry, in addressing this important and evolving topic. Now, I'd like to share with you a few projects going on at the Texas A&M Transportation Institute, TTI for short, in the connected and automated transportation space. Next slide, please. So I want to begin by discussing our connected work zone project in Central Texas. On average, 125 road construction workers have lost their lives annually in the US over the last decade, with an average of 14 lives lost in the state of Texas each year. Now, to address this scourge, TTI has been tasked by TxDOT with a multi-year project to develop and deploy traveler information, mobility coordination, and work zone safety for a 96-mile, $2.1 billion construction project on Interstate 35. TTI has created an innovative, connected, real-time travel information system that provides pre-trip and en route travel information across multiple outreach channels. Now, the device shown in the photo on the left of the slide is the TTI developed Anonymous Wireless Address Matching System, or AWAM. Now, this is a traffic data collection technology that reads unique addresses from anonymous wireless devices, such as Bluetooth-enabled devices from vehicles, and measures the travel time between 2 points along freeways and arterial roadways. This connected corridor has gained state, national, and international recognition, setting the stage for future research and deployment projects in this area. Next slide, please. TTI is a partner in the Connected Freight Corridors project implemented by TxDOT in the Texas Triangle, which is shown on the map in this slide. This triangle contains 3/4 of the state's 29 million person population, which, by the way, is growing at a rate of about 1,100 persons on a weekly basis. 7 of the top 25 national freight bottlenecks are also in this triangle, and it's expected to double freight tonnage from 2010 to 2040. The project vision is to equip the Texas Triangle with connected infrastructure technology, equip 1,000 trucks and Texas TxDOT fleet vehicles with onboard technologies, and to provide freight operators and drivers with information and warnings to improve safety and mobility in the triangle. Next slide, please. So as you're all aware, a data tsunami is underway in transportation at a scale unseen in history. Transportation has become a data-driven industry. As a matter of fact, many of y'all have heard that data is the new oil, which we pretty much need nowadays with the gas prices as they are. But I digress. Said another way, a highly computerized high-end vehicle now uses 100 million lines of code. And for example, the space shuttle used 400,000 lines of code. Now, over the past year or so, TTI researchers have been exploring a wide range of innovative applications for connected vehicle data that has been collected through cellular 4G, principally LTE connectivity. TTI has licensed several data sets from a particular OEM that is popular in Texas, as this OEM's connected vehicles represent about 5% of the total registered vehicles in Texas. So through that, we have access to more detailed vehicle event data beyond just vehicle position and speed, which is going to enable some revolutionary improvements in how we understand and manage traffic planning, operations, and safety. Now, the list of applications on this slide is just the beginning of how connected vehicle data can be used to inform decision-making. Next slide, please. So TTI CAMP. So TTI is a subcontractor to the Crash Avoidance Metrics Partners, or CAMP, a consortium of automotive manufacturers, including Ford, General Motors, Honda, Nissan, Hyundai, and Volkswagen, conducting field experimentation of wireless interaction between semi-automated vehicles and advanced traffic signal equipment. Using TTI's smart intersection at our Rellis campus, the project involves providing strings of equipped vehicles with information from the infrastructure, signal phase and timing, and queue information, so that the vehicles can optimize their trajectory through a corridor to minimize the number of stops and stop times. TTI's Proving Ground allowed CAMP to discover and resolve technical issues in the safety of a closed facility prior to a real-world deployment of this technology in the Houston region coming up on March 30. And I'd like to point out that the University of Michigan Transportation Research Institute is a partner in this project as well. Next slide, please. So autonomous vehicle and roadside safety test beds, and this now says, of course, automated vehicle, and we'll be focusing on the need for clarity with the usage of those terms in ITS America for the coming year. TTI's Proving Ground will be enhanced soon, as the A&M system is in the process of installing 2 independent 5G networks on the test tracks at the Rellis campus, where TTI is located. The network, which will cover 2.5 miles, will provide additional opportunities for connected and automated vehicle testing and smart infrastructure research projects. Next slide, please. So now I'm going to talk a little bit about our expansion into electric vehicle battery testing and impacts on the power grid. Battery-powered automated vehicles will be a part of the future. And I want to mention this project that's at the nexus of the integration of electric and automated vehicle technologies. TTI is seeking to become a national leader in assessing and testing vehicle electrification and its impact on the electric grid in partnership with our sister agency, the Texas A&M Engineering Experiment Station. A planned expansion of TTI's existing environmental and emissions research facility, to be completed in 2023, will provide capabilities in researching and testing electric vehicles, testing batteries at extreme temperatures, and exploring battery range and storage options, as well as charging alternatives. Now, a key focus of the expansion will be evaluating the impact of electric vehicles on Texas and the nation's power grids. Last July, for example, a startup company for electric vehicle charging demand software technology was spun off based on TTI research. This company Electrotempo Inc. uses software technology to predict light-duty electric vehicle charging demands, costs, and locations. And slide 8, my final slide. Now, I'd like to close with this slide, and I've been using this for years, as I believe we're on the leading edge of the deployment of a fully connected transportation system to include all of the elements shown in this infographic. We're undergoing a transformation. Sorry about that. I had myself on a timer and I'm just at the end. So we're undergoing a transformation similar to the introduction of the Model T car into a horse and buggy world, peppered with bicycles, pedestrians, trolleys, and scooters. So the state of CAVs is positive for certain, but is evolving and still very much in a development, testing, and acceptance mode. So hang on for the ride. It's going to be fun, and it sure has been over the past decade that I've been involved. So thank you so much for your attention. I'm going to turn it back now to Kristen.
Well, excellent work, Greg, Henry, and Lily. I'm going to invite our amazing research leaders to come back and join me on camera. There have already been some really interesting questions through the Q&A function. I want to appreciate our colleagues for already taking the time to answer them. I think the visuals are so powerful, Greg and Henry and Lily, in understanding both some of the challenges we're facing, but some of the amazing progress your institutions are advancing. We've had several questions from our audience, and I'm going to start with one which is in the Q&A box, really to ask a follow-up question to Henry. Henry, could you talk a little bit more about the challenges and differences you're seeing in that traffic flow model and the augmented reality simulations? The audience member is asking, can you maybe explain a little about your hypotheses about why there's such a difference between real world scenarios and the simulated scenarios? And the audience member asks, is it maybe a difference in car following behavior or lateral trajections? Could you just speak to a little bit about that?
Yeah, that's a great question. I think one of the difficulty we're facing for testing and training automated vehicle is that is particularly for these corner cases, and as I mentioned, and the traditional traffic flow model I would say in the traditional traffic simulators, they're all based upon these car following models, lane changing models, and gap acceptance models, and all these models are developed for the purpose of analyzing traffic flow. And so it's collective behavior of traffic. But now when we like to do the testing and evaluation of automated vehicle, we're really focusing on these individual vehicle behavior, particularly for these corner cases. And I'll give you just one more example on these. And one of the interesting things we might want to test for automated vehicle is on an unpaved road and with cars on the side, with park on the side. And then there's, let's say you only have one lane in the middle, and then on the opposite side, there's a car, human-driven car is coming, and then the automated vehicle should wait until the human-driven car, pass by and then move, or what's the rules? And that's not being defined in the traditional traffic simulator. So that's why I'm saying you can't really just utilizing these traditional microscopic traffic simulator to test and evaluate automated vehicles, because for the most part, for most of these regular driving situation, the automated vehicle, the deep learning model can handle it. What is more important for that, for testing and evaluation of these vehicles, is these corner cases, these low probability event, which is not being presented in these microscopic traffic simulators. So that's why we developed what we call naturalistic driving environment simulators.
Fascinating.
If I could add one thought on this, is that in traffic simulation with conventional vehicles, we consider driver behavior, and driver behavior varies enormously. But for autonomous vehicles, we rely on algorithms that were developed by engineers, and they are much more, in some sense, limited or specific, but because also they are proprietary, we don't know what they look like. It would be great if we had data where we would have those kinds of algorithms, and then we could develop much more accurate car following models. But the data are not available, and the data databases are not open for researchers like Henry and I to extract autonomous vehicle information and look at car following and lane changing. Thank you.
Fascinating challenges, right? We're seeing, what I'm hearing is there are use cases even in the human operated world that we still have troubles solving. And so that's just amplified, right, by an automated future. Well, some of those challenges you referenced, everyone, including you, Lily, on some of the active transportation users and what we call vulnerable road users in our system. And so we had a question emailed to us by one of our participants asking, what are safety applications that we're already using that have prevented collisions with cyclists, pedestrians, and other people with assisted devices like wheelchairs or canes? And the follow-up to that question, is there research and development on connected and automated technologies that helps to avoid these collisions that would eventually result otherwise in serious death or injury? And since I'll ask anyone to participate, but we haven't had a response yet from Greg, so I'd welcome Greg to go first if he wants.
No, I appreciate that, and that's a terrific question. You know, certainly we saw in Europe that they took the lead with respect to protecting pedestrians, but vulnerable road users writ large present a vexing challenge, not just for automation or connectivity, but for OEMs, since they literally started to roll on our roadways. So the interplay between those vulnerable road users and the automated or vehicular traffic streams have been a historic problem. We all know that the pedestrian numbers are going through the roof. So I think we're starting to see technologies, and I wouldn't necessarily put this in the automation category as I would ADAS, but we're starting to see technologies that can identify pedestrians and bring vehicles to a halt, before any kind of collision or impact using automatic emergency brake systems. So some of the technologies that are out there now are designed to work more cooperatively with those vulnerable road users. I would say bicyclists and pedestrians. But here and certainly in our university communities, we get students coming at us at obtuse angles on all manner of contraptions, and that presents even more vexing challenges. But it's a significant area of research for OEMs and researchers that will continue to improve, but it is starting to make progress.
Lily, Henry, any responses to that question?
One quick response that this is such a difficult problem because of the challenges that I talked about. The accuracy of the location. We don't have accurate enough location for pedestrians, for vehicles. Our communication capabilities are not fast enough to provide that warning. Our user interfaces are not there to actually provide that warning to a pedestrian. So if you're looking at your phone, you need to have 100% reliability in order to trust that warning that you're going to get. So I haven't looked at the data of how many collisions may have been avoided, but it is such a difficult problem. We're starting now a project with FDOT through the US DOT through the AID project to look at midpoint or mid-block warnings for pedestrians. But from what I've seen, it's just a really, really difficult problem.
I totally agree. I think it's a very hard problem, but I think that technology is being developed to so we're making progress in terms of technology development to help address some of these issues. And one of the things we do for our smart intersection project is to instrument these roadside perception sensors so that we can detect and track the road objects. And these objects could be vehicles, could be pedestrian, could be bicyclist. And from the detected object information, we can broadcast this information and to connected vehicles to warn and these vehicles to some of the impeding dangerous situation. So we're making progress, but it's still we have long distance to go, I think.
And Krista, maybe a back end observation. As we sit here today, it's all about conspicuity, right? So right now, there really is no substitute for humans paying attention to what they're doing, but making sure that the vulnerable road user is as conspicuous as possible. There's just no substitute for that. But back in the connected transportation days when I was with USDOT, we were aware that in Japan, for example, they were testing chipsets that were put in school children's backpacks so that they could communicate their proximity to vehicles using the same communication channels. At the time, it was that 5.9 gigahertz DSRC. So that's how the V2X concepts became, kind of de rigueur. It's not just vehicle to vehicle now, it's vehicle to everyone, including vulnerable road users. So that idea is out there. It needs to migrate with wherever the technology finally lies.
Well, thank you for bringing up that conspicuity and how it takes really a whole systems approach to this, Greg. And conspicuity is a very interesting topic this week as daylight savings, right, is being debated at Congress, because we know that some of these fatalities and serious injuries happen in dark places, which shows the importance of policy and policy development. So I want to go to the next question from one of our members, which is a really interesting one. And they ask, one implication of connected and automated vehicle technology development is that infrastructure can be used more efficiently. And you just shared a few examples. So they follow up by asking, what is your suggestion for the use of some of these new funds in the new Infrastructure Investment and Jobs Act, and maybe any of the programs that you're looking at in this amazing and historic investment? Anyone want to start first? Lily?
Sure, I'll take a stab. One of the big challenges for this is that we have private sector and public sector trying to come together and coordinate. In theory, that would give us the best outcome. Now we're talking about two different cultures. Anecdotally, I'll tell you that with FDOT, we've had so many meetings with industry, with OEMs, and FDOT was always asking, what can we do with our infrastructure? What would you guys like? And we, the thing that we got most frequently was, well, we need better striping, or we want to make sure that the striping is in place, which is, kind of limiting in some ways, in that, we can get the most benefit from those technologies if we have both CEV, both connectivity and automation. This is clearly the direction we want to take, but this requires collaboration from very different cultures, and that's what makes it difficult.
I can't agree. I can't agree more. It's absolutely, Lily, you're absolutely right. I think it's one of the difficulty I see in the connected automated vehicle space is that AV developers or vehicle developers, they don't want to rely upon infrastructure because then the system becomes so complex, and then whether this the reliability, the accuracy, all of that issues will come up, and then but to address these issues related with safety, particularly for automated vehicles, however, it's that we most likely we will need support from infrastructure and to be able to have a large-scale deployment for automated vehicles. So that's sort of the I think that's sort of the difficulty we are facing. And one of the things I am going back to my smart intersection project. One of the things we like to test out is that how can we trust these sensor data sharing messages coming from the roadside. And so if the vehicle side cannot trust these messages, there's no way these will be really helpful for automated vehicles. And so the first thing for us is to test the trustworthiness of these messages. So before we deploy these sensors on the road, so that's why we install all these sensors in MCD test track, and we develop a set of scenarios to test the accuracy, the reliability, the latency for the communication and things like that, so that we can confidently send that messages to the automated vehicles and for them to use it to help them.
And Kristen, I would just say uncertainty begets hesitancy, right? So the FCC did this industry a huge disservice by sowing confusion into the technologies that would enable vehicles to talk to infrastructure and to other vehicles and the vulnerable road users. So that uncertainty has caused OEMs to back away from working collaboratively on what the next step is from a connected vehicle future. And by definition, municipal, state, and local governments that are already cash tight are not going to be looking to invest in infrastructure to communicate to vehicles that aren't even in the stream of commerce, if you will. So this chicken and egg dance has been going on between infrastructure and vehicles for the entirety of this technology development. But then you drop a bomb in the middle of it with this confusion over spectrum. And now it's just at a complete state of equipoise between OEMs and infrastructure owners. And they're not going to make the investment absent knowing that there is a cohort of vehicles with which they can communicate two-way, right? It's a symbiotic relationship. I agree with Henry that the OEMs don't want to rely on it, but there are benefits that both can attain if they have the certainty on both ends.
Thank you so much, Greg, Henry, and Lily, on that challenging but very important question. And then, of course, as an ITS America representative, that shows the value of organizations like ours that bring these institutions together to help ensure that the federal government is informed when they're making these decisions in the future. Thank you so much. We have just a few more minutes and we're going to have time for 2 more questions. Everyone, if you do want to follow up with any of these amazing thought leaders, we will make your questions available to them. So thank you again for convening today. The second to last question is about planning. A lot of this is not just reactive, right, to technology advancement. It requires an enormous amount of planning. And so there's a great question from one of our participants today asking, as we see the bills and the projects and research coming up, how do we help plan together to enable for these connected and automated technologies? Is there any other planning research or any planning thoughts or tips you would like to share with this group?
Well, I think the power of community, through principally organizations like ITS America, but others that gather in this space, because there's no competitive advantage to safety. I think we all agree on that. But the power of united voices from many different industries, many different academic organizations, governmental entities, is what captures the ear of stakeholders, right? I mean, it's important that the public understand what these technologies promise to bring, but that gets nowhere if we don't influence the stakeholders in the legislatures across this country to make the bold decisions and the correct decisions to save lives on our roadways. It's beyond irresponsible that in excess of 38,000 Americans are lost on our roadways on an annual basis. That would be intolerable in any other instance.
Christine, one thing I'd like to add to Greg's point is that I think just from planning perspective, I really think the government should take a lead role on that, because as Greg mentioned, uncertainty create problems, right? So people can, if there's uncertainty there, the OEM may not want to invest, the local agency may not want to invest in this. And so the federal government particularly, I think, need to take a leading role on this type of situation. And so that, and with certainty, then people can start to put their confidence in it. They can start to move towards the same goal. But otherwise, there's, this field is fast evolving field. So there's so much going on in this field, not only in the technology development, but also in terms of the investment world, in terms of the collaborations between different type of, the legal issues and all of that. So I think that in order to create some sort of certainty and to move this in the right direction, and I think the government needs to take a leading role. And obviously, when Greg mentioned the FCC's new ruling, that certainty essentially stopped a lot of these investment and development of it.
Lily, is there anything you'd like to add?
Yeah, I completely agree with what Greg and Henry just said. We need clear direction. The DSRC is a very good example of what happens when there's no clear direction and there's confusion right now across the country. So there has to be some agreement and for the direction.
Well, Greg, Henry, and Lily, thank you for this amazing discussion today. Thank you to our amazing engaged participants. We had so many more questions and thoughts in our chat box that we could not get to today, but I'm going to try and summarize them into a last lightning round challenge question for our amazing thought leaders. So starting with Lily and then Henry and Greg, in 30 seconds or less, what is one thing that you would like to see from our federal leaders in this space? Lily.
Well, I would like to see more funding and engagement at the local agency level, because that's where most of the changes can happen, most of the deployments can happen, and we are very lucky to have the city of Gainesville. They're just a wonderful partner. They're very often, they don't have the resources to help, but they could make a huge difference with the right type of resources. So I hope that the federal government can provide more resources at the local level. Thank you.
If there's, Christine, if there's one thing I want, I think I'd like to have the 75 megahertz of safety band back.
We'll work on that, Henry. That's a great one. Greg?
Well, I would certainly say, from a federal perspective, I'd like to see respect for our international partners. Connected vehicle research was a global enterprise. The Americas, Asia, and Europe through Ertico. So the fact that the U.S. Didn't hold up its end of the bargain created a global enterprise, and that's going to have repercussions with our standing internationally, particularly in the research space. And also, I'd like to see the federal government get serious about spectrum policy. I mean, not only was DSRC undermined, but another key technology that underlies not only connected vehicles, but whether or not even automated vehicles will be able to perform is GPS. And the spectrum for GPS has been under threat for well over a decade, and there has been no meaningful investment in a complementary or backup system or shoring GPS against jamming, spoofing, and intentional acts of bad nation states.
And this, everyone, is why these are the thought leaders in the United States. Lily, Henry, Greg, thank you so much for your time, for the work that you do, the leadership you provide. Thank you, everyone, for joining ITS America as we kicked off our 2022 research series. We will have our next research topic focusing on transportation equity in late April, so stay tuned. And thank you again. Please give a round of applause to Lily, Henry, and Greg for their time and thought leadership. Thank you all. Have a wonderful week and happy St. Patrick's Day.